The third chapter is the climbing performance, and the first section is climb angle. When we analyze the climb performance, there are two concepts which are very important. The first is angle of climb or climb angle. The second is rate of climb. So immediately after the takeoff, the angle of climb is crucial in order for the aircraft to avoid high terrain or building close to the airfield and to minimize noise disturbance on the ground. So there's two considerations. One is to avoid the tall buildings or the hills. The second is more environmental consideration, that's a noise. And that's when the aircraft immediately after takeoff. And once the tall buildings or hills are cleared, then the priority switches from the angle of climb to the rate of climb. So the priority for the rate of climb is for the aircraft to reach its optimum cruise altitude and speed in a manner which is most efficient in terms of minimum drag. And let's first look at the angle of climb. Before we do the calculation of the angle of climb, let's first look at the climb gradient, which is showing as gamma, and it's also usually measured in percentage. So climb gradient is defined as the change in height with respect to the horizontal distance it traveled. And remember, it's also usually measured in percentage. And so we want to get the climb angle or climb gradient gamma. So in order to do the calculation, we need to first see the equation of motion. I've actually seen this equation before, and we have this aircraft in the climbing position. So it's pitching nose up along the climb path, and the pitch angle is theta. And along the fuselage direction or the climbing direction, so along the flight path, we have thrust, we have drag, and also we have the component from the weight. So T minus D minus W times sine theta. Theta is the pitch angle. Actually, it's a climb angle here. W on the right-hand side of the equation along the flight path is acceleration along the flight path. And that's one equation. And also now let's look at the direction normal to the flight path. We have the lift L minus the component from the weight W times cosine theta. And the acceleration, and you can see the acceleration is actually W over G, that's M, the mass. And what is V squared divided by RC? So, and that's actually the centrifugal force, and RC is radius of climb. And actually we can take the climb as it's doing a circular motion. And before we move forward with the equation of motions, now let me introduce another concept, that's T minus D divided by W, and we usually call this excess thrust to rate ratio, and it dictates this quantity dictates a climb angle that can be achieved. For example, a fighter aircraft with this T minus D divided by W with 1, and this aircraft can climb vertically. If it's larger than 1, the aircraft could also accelerate its airspeed while flying vertically. And usually for the majority of aircraft, it's far smaller than 1. And the steepness of the climb angle strongly depends upon the drag, which in turn depends on the efficiency at which the lift is produced. to maximize excess thrust. So if we want to have better climb performance, we want to maximize this excess thrust. And an aircraft should therefore climb at a speed where the drag is minimized. Does that make sense? Because we want to have this T minus D divided by W larger. So in that case, the D should be smaller. And that's why we need to let the aircraft climb at a drag which is smaller. This is an important graph we need to understand. So the horizontal axis is airspeed, and vertical axis is thrust or drag. And we know the drag has two components. One is a parasitic drag, the other is induced drag. And the parasitic drag increases with airspeed, but the induced drag decreases with airspeed. So you can see the parasitic drag and the induced drag, they have a cross-sectional point at somewhere correspond to an airspeed. And also we know from the taking off procedure, we know the thrust decreases with airspeed, right? Okay, so you can see the thrust decreases, assume linearly with the airspeed. Okay, so we know the trend, and we will do this analysis later, further. Okay, now let's go back to the equation of motion, and we want to get the climb angle gamma. And so this is the equation we had derived just now. And so now let's do an assumption. We have steady climb, and which means there's no acceleration. And that means the right-hand side of the equation motion can be set 0. So we move W times sine theta and W times cosine theta to the right-hand side. Then we have the simplified equation motion, or the equation motion for steady climb. And let's further assume that angle of attack of the aircraft is 0. That means the fuselage is aligned with the flight path. So the pitch angle theta is the same as the climb angle gamma. Okay, then, so we know theta can be replaced by gamma in the equation of motion. Then we can calculate theta. Theta can be calculated as x sine t minus d divided by w, and you can see this gamma is purely determined by the excess thrust weight ratio, and we've analyzed t minus d divided by w before. And we know usually for transport aircraft this is far smaller than 1, but for fighter aircraft it's can be 1 or even larger than 1, because for the maneuverability. So now, because thrust is known usually for an aircraft, in order to get theta, we can first calculate the CL to match the W, and then according to the drag polar we can get the drag, CD drag, and then we can calculate this climb angle gamma, or climb rate. And just now we had this graph. Before, we know the drag can be divided into the parasitic drag and induced drag, and at some point with a certain airspeed, they are the same. So at this point, the total drag, that's the addition of the parasitic drag and the induced drag. At that specific point where the parasitic drag and induced drag crosses, and we have the minimum drag. And for that airspeed, we call it the minimum drag speed. So for any aircraft in straight and level steady flight, minimum drag is achieved at a speed where the parasitic and induced drag are equal. And we know the thrust, in reality, it decreases with airspeed. But now let's assume the thrust is constant. And because when we discuss the climb rate, we want to know the climb angle, and just now we derived the climb angle is determined by the excess thrust ratio, that's T minus D divided by W. So we want to maximize T minus D. So if that's larger, then the climb angle can be steeper. And so we assume the thrust is constant or independent from the airspeed, and then at which point we can get the maximum excess thrust. So that's when the aircraft is flying at the minimum drag speed. So the gap between the thrust and total drag is the largest. And for climbing flight, if thrust is assumed to be reasonably constant, then the speed for best angle of a climb, Vx, is close to its minimum straight and level drag speed. And climbing at Vx maximizes the altitude gain per ground distance covered. That's a climb gradient. So we have a very important quantity introduced, that's Vx. Vx is the speed for best angle of climb. So at this angle, we have at this speed, we have the largest excess thrust. That's T minus D is maximized. That's because and the drag is minimized. In this case, which case the thrust is assumed to be constant. Now let's move to a more realistic case when the thrust decreases with airspeed, which is more realistic. And in that case, we can see the maximum excess thrust, that's a gap between thrust and the D total drag, is shifted towards the left-hand side of the V minimum or minimum drag speed. So the Vx is no longer the same as V minimum drag speed. That's because the thrust decreases with increasing airspeed. And now we should know the importance of Vx. Vx gives us the largest or maximum excess thrust. And in here shows the different segments of the climb. So we first have the ground run, and the first segment, actually the first segment is when the aircraft from liftoff to achieving the screen height. And the second segment showing here is when we are looking at the climb angle. So the aircraft want to clear any high buildings or hills or obstacles. So that's the second phase. And the third segment is level flight. And finally, it goes to its usually from 400 feet to 1500 feet. So that's the three segments of the climb. And here is one engine inoperative case. That's the FAA regulations for climb gradient with one engine inoperative. So you can see there's some requirement for the climb gradient, and I'm not just reading through these numbers, but you can generally see the gradient. Climb gradient is quite small usually. And here are some descriptions of each individual phase and the corresponding aircraft configurations, and also with the climbing gradient showing on the right hand side of the table.